Okay, we're going to go ahead and kick the meeting off. Apologize in advance to anybody who was trying to watch live. We had some technical difficulties, so the stream was about 10 minutes delayed. There's a recorded copy of it, so I'm going to edit that and put it up on the YouTube channel a little later, make it look nice and clean. I don't have very many things to go over. There is an IP Network Security Part 2 webinar on November 15th. Those are always extremely informative. They count as credits towards your recertification, so if you have a certification, it's $55 for members and $85 for non-members, and aside from the certification portion of it, they, again, are very informative. The SBE National Meeting is going to be streaming live on October 27th, so if you can't be there in person, you can always watch the stream. There's more information on the SBE website, sbe.org. Our Christmas party is on December 12th. That is the party that we have every year with SMPTE, AES, and SSPI. It is members only, and there is a little fee associated with it. I'm going to have an email that's coming out in a couple weeks with more details on that. So without further ado, I'm going to introduce Ben from Jampro, and he's going to give his presentation.
Hello. Okay, after a few technical problems, it's not like we're in a broadcast sort of situation. We've managed to fix it, and we're back on. Anyway, so my name's Ben Crease. I'm with Jampro Antennas and Alan Dick. Jampro's an North American antenna manufacturer based in California, and Alan Dick does a similar thing in the UK. Today I'm going to be talking about some of our broadband solutions, particularly antenna broadband solutions, show some of our experiences on where we've deployed digital signals very similar to the ATSC3 standard worldwide, and also talk about single frequency networks and how ATSC3 will allow you to use that and how that may be a benefit to you. So I'm just going to talk a bit about the history of the company, some of the SFNs, and then some of our experiences. Jampro's one of the oldest broadcast antenna and combiner companies in North America. Been around since 1954, so over 60 years. And it's the parent company of Alan Dick Broadcast, which is one of the oldest, or if the oldest, combiner and tower company in the UK. And it was originally from EMI, like EMI Records. It was originally part of the EMI group in the UK. The installation base that Alan Dick has in the UK is very large. It's on the majority of the sites that are owned and operated by Arqiva, which is the main infrastructure owner in the UK. As I said, the company delivered its first systems over 60 years ago. We've been doing television systems, circularly polarized televisions, circularly polarized TV systems. We pioneered some of the technologies from in the 60s and 70s and been providing solutions on that. And we provided something like 35,000 broadcasters worldwide have benefited from the joint systems from Jampro and Alan Dick. And as a North American manufacturer, we have a truly global presence. We do a lot of business internationally. In terms of our capability, it's very much we go from the output of the transmitter to the top of the tower. That's really where our expertise is. So we provide antenna systems, combiners and filters, mask filtering, rigid line, waveguide, towers, and we install and commission those all around the world. In terms of where we have offices in North America, Mexico, Canada, Sacramento. We also have the Alan Dick office in the United Kingdom. We have some satellite offices in the Middle East, in India, and also offices in Thailand, which look after Asia. So with the offices all around the world, we have someone working about 24 hours a day. So if you do need to contact us, we do actually have offices open 24 hours a day. In terms of engineering design, we have various structural and RF softwares to help us design antennas and also the mounting brackets, etc. for antennas. We use HFSS, which is a RF modeling program. We're finding that's a very good tool. We also have physical test range, which we do measurements. We're finding the HFSS is normally gives very accurate results. And we have other other softwares as well. Alan Dick wrote an in-house software program called Antenna Array, and this is a program that takes real live measured data from individual panels in particular, and then it can take that into a mathematical model where it can simulate multiple panels pointing in different directions with different power levels, etc. And it will generate the azimuth and elevation patterns in a very accurate manner. And it's been used by in conjunction with Arqiva in the UK, and Arqiva own all the sites that companies like the BBC would transmit from, and they take our data and they use that for their coverage planning, and it's been proven to be very accurate. In terms of manufacturing, we are really very much a manufacturing company, and not just assembly. We manufacture predominantly in North America, in California, and we also do some manufacture in the UK. We manufacture virtually everything we provide. There's a few finishing procedures that we don't do in-house, but we still keep in California. We don't do anything in China or Mexico. We try and keep it under our control so that we can maintain quality and delivery. In terms of production, we do various UHF and VHF and FM projects around the world. And the volumes can go up and down on a given year. But if, for example, the repack is going to happen, I think everyone's production is going to be very stretched and we'll have to expand rapidly. But this gives an idea of roughly what we can supply in a kind of average year. Maybe 600 panels, UHF panels, and various number of combiners and filter systems too. So just to recap, why Jampro and Alan Dick? We're very qualified companies in both North America and the world. We've got many systems on the air. And some of the highest power UHF systems in the world have been provided by Jampro. I'll talk about that a little bit later, one particular project, which is this antenna here. And a lot of these systems are broadband. This is very high power and broadband. And that's something that certainly in North America, most of the manufacturers here haven't got so much experience with. It's typically narrowband, and the high power is maybe not such an issue, but being broadband is something that's not typically been required in North America. But with the changes, ATSC3 and maybe the repack, having broadband solutions I think are more and more relevant. The only other thing to say is our experience with TV antennas and some of the issues, particularly with the digital transmission, has also allowed us to improve our radio products, our FM products, where some of the stresses that cause a failure point in an antenna, traditionally your failure point would be melting. If you think of a piece of coaxial line, it gets too hot and the inner melts. But with digital signals, the voltage generated for a given power level is much higher, and the failure mode can be arcing, can be a voltage problem rather than a current problem. And so where you may rate something with a given power rating, you may find the failure point is voltage. And so that means maybe you need a design change to either maintain your power rating or you need to derate accordingly. And that procedure of reassessing existing designs has also, whilst we had to do that on TV for digital, it's also allowed us to do that again on our radio products and make sure that any potential weakness would be removed. So considerations for a digital signal frequency network. One of the things I like to talk about here is what I call where your audience is. By that I mean a traditional broadcast network, it's a kind of fixed, you expect your broadcasting to households. But with ATSC3, which is on a COFDM signal, you have the opportunity to maybe change your modulation parameters, and maybe that will help the receivers in mobile or portable devices get a signal. It doesn't change the RF level necessarily, but it does change the signal to noise ratios that you need to achieve to actually complete your transmission path. So these are the three sort of different audience situations that occur. It's fixed reception, which is like a traditional analog signal or ATSC1 signal, where it's really to the household and it's to a rooftop antenna. And then the two other kind of situations that we see is portable outdoor. So that would be to a car, for instance, or maybe a mobile handset, but outdoors, and then a mobile handset indoors. And the different applications can mean that you need different RF levels to achieve to achieve reception if a given modulation parameters are the same. If you change the modulation parameters, you can also change the RF levels that are required. And in terms of digital standards, why this is relevant, you have DVB-T or T2, which is used in many countries, Middle East, Africa, Asia, and Europe. And you have some other standards like ISDBT, which is used in Latin America and Japan, slight variation in Latin America. And what ATSC3, the key thing is all of these are OFDM signals, which means they operate in a similar way in an RF environment. Whilst the standards are different, the ways they work and the ways they can be applied are quite similar. So our experience that we've had since, well, over 20 years experience working in digital, probably first experience was in the UK when they first went digital. The issues that we came across are still very relevant to the signal that ATSC3, for example, is going to produce. So this is just explaining about the three different scenarios and what that might do to the signal strength that is required if you stick in a single modulation scheme. So in a traditional rooftop situation, you have a receiving antenna which has a gain. In this case, if we look at the UHF figures, it's 11 dB, and that's at 10 meters or 30 feet high. And for want of an arbitrary number, 56 dB microvolts is what is required for that system to work. Now, if we then go to a situation where we're portable outdoors, two things happen. One thing is the antenna now is omnidirectional, so you have no antenna gain. And you tend to have, you don't tend to walk around at 10 meters high, so you're typically at street level, so 1.5 meters, 5 feet high or so. And so those two in combinations mean that you're probably lost about 20 dBs in your transmission path, essentially. And then if you then take it to the final scenario where you'll be portable and indoors, you have to have another 10 dB to get over the fact that there's building penetration loss. So overall, compared to a traditional rooftop solution to an indoor portable, you're maybe 30 dBs different. So that's 1,000 times the signal difference. So in terms of pure RF power, if you're using the same modulation scheme, it's going to be very hard to achieve that in your same coverage area. You either just accept that it's only going to work in a very small area, or you need to look at other solutions to maintain that RF level. And as I said, you can change the modulation scheme. That will give you some benefits as well, but it's probably not going to get you 30 dB. It may get you some way. So in terms of OFDM or COFDM signals, there are a number of modulation schemes, as I say, that as a broadcaster you get to decide to use. There's actually many parameters, but there's certain sets which work together to give certain effects. One of the effects is you can push in this direction, which would maybe increase your bandwidth. I think ATSC3, the maximum payload is 56 megabits a second. If you go full bandwidth, I think it's 496 QAM and everything else in the modulation. And so it can have a very high bandwidth. It can also have a very good performance for handsets, high moving signals, where if you're traveling too fast, you get a Doppler effect. So you can set a modulation that has essentially a more robust signal, certainly with regards to speed, so that the handset, even if it's traveling in a car at 100 miles an hour or something, you'll still be able to receive a signal without it having problems. And it can do that as well as an OFDM signal. But the key thing is it can't do that at the same time in the same service. You kind of have to say, well, I'm going to go high bandwidth, or I'm going to go high speed reception, or I'm going to go somewhere in the middle and compromise. And the same as the robustness of the signal. And it can also affect the size of your SFN. So all of these things need to be considered when you're picking your particular modulation scheme. Now, the benefit, one of the good things with ATSC3, which isn't always the case in all of these digital modulation schemes, is that within your given RF frequency, within your 6 megahertz, you can actually set up different services. So within the same transmitter, you can set up different services where, for example, you could do a high bandwidth service, which would be maybe your ultra high definition or your high definition signal. And you can also set up a standard definition signal, which was maybe a more robust signal, and then a mobile service, which would maybe help with the Doppler effect, and some other data services. So you're not limited by what you can do within your individual transmitter, but each of those services has to stay within that modulation scheme. And it's, whether you transmit the same program over all these different modulation schemes so that you have an HD, an SD, and a mobile signal, or maybe you think the content on mobile may be different to have it more focused to a smaller handset. As broadcasters, that's your choice. We're just here to give you the technology and how that can be used. And again, the key thing here is if you change those modulations, your coverage area in terms of where the particular device will be able to receive the signal will change. It won't change the RF signal, that's fixed, but this is like a receiving, chance of receiving. And that's a little bit different from the traditional broadcast, where as broadcast engineers, we care about RF field strength. That's still important, but we also now care about where you receive a signal. And a lot of this concept sort of comes from the cellular industry, which is maybe not surprising because they deal with mobile handsets all the time. And in terms of a single frequency network, so what this means is you have your license and you have a given area you want to cover. Traditional broadcast, you'll have one site, you'll maximize the ERP to your license, and you'll cover the area and you get what you get. The single frequency network, the key here is you're using multiple locations to transmit, but it's the same frequency. It's not a different frequency, you're not doing some clever frequency shifting. It's all on the same frequency. Now, of course, traditional analog systems, if you do that, you're going to interfere. You're going to have areas where you hear both signals or you can see both signals. You're going to have ghosting, and it's going to be a complete mess. But in a single frequency network, the maths works wonders, and as long as the signal's set up properly, you have a suitable network, the signals will essentially arrive at the same time, and your receiver will be able to make sense of all the different signals and pull out the signal. And where you actually have overlapping areas, you can have gain. The exact gain is maybe a little bit debatable according to the network. Sometimes you get gain, sometimes you don't get much gain, but you don't actually get a negative effect, so you don't have an area where you can hear both signals. So this changes from an RF level to more of a network issue.
I was going to comment real quickly. There's about 20 single frequency networks on the air with ATSC1 now. It can be done with the ATSB signal. And there's a big one in Missouri that uses Jampro Antennas.
Okay.
It's the copper thing in Springfield.
Okay. So, it can be done on ATSC1, but it's not so prevalent, and you're somewhat limited in what you can do in some ways.
You have to synchronize the exciters, the randomizers, and there's just one guy that's got the patent of that, and you got to buy the equipment from him, and that's Merrill Weiss.
Okay.
He's got the Penn State and various other stuff around. Was the first one, and then there's one in San Francisco for TVS Tech. It just went on the air.
Okay.
But ATSC3 makes it a lot more flexible.
Yeah. So the key thing is, whilst it's not impossible with any digital signal, in theory can be SFN'd. It's pretty difficult with FM radio, like impossible. But basically, the more carriers you have, the more kind of maths you have to play with to make it work to your advantage. And this is a kind of slide to show how this works. From an RF point of view, all of these are the same frequency, but within the information within the particular RF stream, you have something. In this case, it's called cyclic prefix. But essentially, what that's saying, it's a bit like a packet system where you're sending this bit of information out. But as long as it arrives within the given time, all of these add together. If this signal was a bit later, then this signal will actually interfere with the other ones. So that's the kind of simple concept. So the different sites do have to be time synchronized, typically a GPS time synchronized. Or if they're not time synchronized, they have to be set in a network so that you don't run out of time, essentially. Like the signal will get to where you're trying to get to without becoming an interference signal. So again, the main benefit is more efficient utilization of the spectrum because you're either expanding the coverage or maybe you're just increasing the RF signal within the coverage in a more controlled way, but on the same frequency. So where you have overlapping coverage areas, you will have this kind of so-called gain, or certainly not a negative effect. And if you move from one coverage area to another, the receiver is independent of that, or it doesn't see that. Essentially, it's just you have a different shape coverage area, and the levels are different if the network's set up properly. And so the question then is, how do you, if you want to do an SFN, how do you achieve that as an end result? There's a couple of approaches you can take. If you really care about your results and you absolutely want to guarantee it, then you want to get a consultant and someone that knows how to set up a single frequency network, and they'll use some software. And that's a good way of doing it if you really want a good network and you want to plan it from day one. Obviously, we all have budget constraints as well, and so you may want to take a different approach, which is maybe you just copy your existing system and you worry about the other SFN sites later. You maybe at least set it up so that the SFN is possible in the future, but maybe you turn your main site on and you say, oh, let's see where we have problems, and if we have a problem, then maybe we drop in a repeater site. Obviously, that has a more chance of not working perfectly, but from a budget point of view, it may be more suitable for a given broadcaster. And let's be real, also landscape change. We were having a conversation earlier where you may have a good signal now, but if you're in a thriving city, people may be putting up very large buildings, so where you didn't have a problem now, you may have a problem in 5 years. But if you have the ability to have a single frequency network, you may be able to drop in a repeater site and cover the area that's since been shielded by a building, etc. And so maybe you go somewhere in between. Maybe you put one site up and put a couple of relay sites in. But the key thing is that you can improve your coverage at a later date if you're using a single frequency network without necessarily changing your license. It would all be within your licensed area. All you're doing is, instead of having one site where the signal rolls off as you go further away from the site, you can pull up the signal in various locations where you put these repeaters, and you still maintain your licensed DRP. So in terms of implementation, this is particularly focused on where we are now, which is ATSC1, to maybe going ATSC3. The one issue in that is that the systems aren't compatible directly. So if you have a transmitter running ATSC1, it may be able to run ATSC3, but it can't do both at the same time. So there's the question of what's important to you. I would have said at the moment what's important to you is ATSC1, because that's where all your customers are. In the future, it may be ATSC3, because some of the benefits, for example, to mobile handsets, and also still a greater data rate for the given RF spectrum, just because ATSC3 is a more efficient encoding anyway. But how do you go from 1 to 3? Because that means you have to dual cast, and as we know, spectrum's pretty limited anyway, and possibly reducing with the repack. So you have to look at how you're going to do that. Certainly, if you need to put another antenna up for a period, you have to look at like the structural capacity of your existing station. Is there any space on it? What's suitable? Or maybe you have an existing system that is broadband in some capacity, but do you have the power rating in that? Or does it have the bandwidth you need if you're changing frequencies? And is it ATSC3 ready? This is really a hint to say ATSC3 does generate higher voltages than ATSC1. The exact figure is maybe a bit debatable, but it's somewhere between 2 and 4 dB higher. So you may have the adequate power rating, but you may find the voltage rating is now a problem with ATSC3. So all of these things that have to be considered. And you can also look at maybe combining frequencies. You may not have 2 licenses, but you may know someone else that has a license, and in combining the two RF licenses, you may be able to have one transmitter on ATSC1 and one on ATSC3, and so you can service both markets. It would still mean that you would lose some of your bandwidth distribution, so maybe you have to turn one channel off or not broadcast it 24 hours a day, but you'd be able to broadcast other channels ATSC3. But I think as broadcasters, what that means is we're going to be forced to work together whether you like it or not, just because there's less and less spectrum to use. Other people value the spectrum, maybe they want it a lot. A lot of the telecommunications companies, they want to buy the spectrum in the repack. So as broadcasters, we'll have less spectrum. So we need to use the more efficient encoding methods like ATSC3 to maximize what we're doing with that spectrum. But in doing that, that may also force broadcasters to physically work together. Whilst there's plenty of political and commercial issues involved in that, we may find that if we don't work together, there won't be any spectrum left to use. And in terms of timescales, when we did the the analog to digital transition, the timescales was maybe 10 to 15 years from when we first started transmitting digital to when we turn the analog off. And in fact, I think analog's still on in a few LP stations, right? Yeah, so we haven't even completely done that. Yeah. So how long?
Gary, have you listened to that?
Oh, I know, yeah, we have a Latino station
Yeah.
in Atlanta on
Channel
channel
6.
So how long would it take to turn from ATSC 1 to 3? Well, probably the answer is infinity, because maybe ATSC 1 will run for an awful long time. I put 3 to 5 years up, but that's probably very optimistic. It could easily be 10 years. Now, as broadcasters, if we work together, we can maybe control that situation where we put the minimum ATSC 3 signal on to start with by working together, and then as the consumers get receivers that work, then we can increase the ATSC 3 and get some of the benefits of a single frequency network and the higher data bandwidth. But the reality is some of this is out of the broadcaster's control. You can try and lead the consumer by putting your best content on ATSC 3 signals, and putting, and maybe putting the less popular content on ATSC 1. But you really only have you can only do it carrot or stick to persuade a consumer to go out and spend some money. So the point here is really both of them are going to be required for a number of years, and that means that you have to consider what that means, and that may have a far bigger effect than the repack. Obviously, in an ideal world, the repack and ATSC 3 will happen at the same time, but that remains to be seen whether that's going to happen.
One big thing that ATSC 3 does is 4K video.
Yeah.
ATSC 1 cannot.
No, well, you have the bandwidth.
So if that's a appeal to the consumers, that may be how you have to go about it.
Yeah, so certainly 4K is possible on ATSC 3. Of course, it also uses an awful lot of bandwidth. So when we're already suffering under bandwidth limitations, if we go 4K, there's probably not enough left for anything else.
We use the new MPEG-5 codec. You
Yeah.
could probably put a half a dozen of them on ATSC 3.
You might, yes.
It depends how high you run it.
Yeah, but and then there's all the other issues. Whilst that may be possible, you're not going to be doing that and transmitting to mobile handsets at the same time. So again, what it means is ATSC 3 gives you lots of choices. It doesn't necessarily give you lots of answers. Is the thing. The answers have to come from the commercial, economic reasons.
So Gary, you got a 4K TV at home?
No.
What's wrong with you?
Okay.
source material. And
But-
I have to watch it this close.
I mean, in terms of 4K, there's obviously 4K cameras that are available on the market, have been for a while. That's not too much of an issue. 4K televisions, a lot of television sets I see are made in Korea, and Korea is pushing very hard for UHD. They're going to probably be on air next year, and they're already selling 4K televisions, and they're using ATSC 3 as a standard. It may be slightly different to what's done here, but it's going to be probably the same chip. So there's no doubt there will be consumer devices that will have an ATSC 3 chip that will do 4K. Whether it will be a mobile handset remains to be seen, but there'll definitely be large screen devices. So probably UHD is a good push for ATSC 3. But again, as a broadcaster, there'll be some that want to push on that. Others might go, let's put, 100 mobile signals into ATSC 3 and see what happens with that. And then you're competing with the telcos and more the sort of services that they provide. But again, it really depends on you as broadcasters or what you want to do. So again, in terms of the transition, I've put this up from the old analog days where you start with analog and you put some basic digital on, and then maybe you assess what's going on, and then you finally turn analog off. Well, going from ATSC 1 to 3 is almost a repeat of this whole thing. Instead of analog to digital, you're going from 1 to 3. So some of the same issues that you came across will be relevant. The one thing here is you're not getting a second frequency. Before analog to digital, you were allowed a temporary digital signal, so you'd have essentially two RF channels. Whereas now you're not going to get that. There's not enough spectrum, even if the FCC wanted to give it to you. So that's going to add an issue into that transition. And again, I think it's going to force broadcasters to work together, or go off the air, or dramatically reduce the programming that they're offering at the moment. But there's definitely going to be some compromises along the way. So that's the main part, the sort of technology part of the presentation. The rest of the presentation, I just want to show some of the experiences that we've had around the world in particular, particularly digital experiences, where some of the products we used have really come from some of the modulation schemes and some of the possibilities that you can get with this digital signal. So this is a product that we think is going to be very important to any moving of frequencies, depending on how much gets moved at the end of the repack. But this is a slot antenna, UHF slot antenna. Traditionally, slot antennas were very narrowband devices. They were maybe one channel, maybe two channels. But we have been providing what we call a broadband slot antenna for probably 15 odd years in various different designs, where we can get over 100 megahertz of bandwidth in a single slot antenna. We provided some that have almost 200 megahertz of bandwidth. It's maybe quite hard to see, but you have a plot here which shows a VSWR of 1.1 or less for maybe 110 megahertz, which is sort of typical of the antenna that we provide.
I have a question.
Yes.
Okay. What's the trade-off? In other words, is there efficiency hit that you take by using a high bandwidth slot antenna?
If you go ultra high band and you really push the limits, like anything, there is a bit of a compromise. You normally find that your elevation performance is maybe fixed within certain boundaries. So you might find that the range of beam tilt and maybe the range of knob fill is a little bit fixed. If you just have single band, you have full control over that. One of the ways that we get maximum bandwidth is we have to fix some of the elevation parameters. But it depends on ultimately the gain of the antenna. If you have a higher gain antenna, you find you probably have more control over that. And that's probably going to be a situation where that's either a massive problem or it's going to be the elevation performance that you wanted anyway. So we can normally find a product that will fit into any elevation profile that you have. Or maybe we reduce the bandwidth slightly and you get your elevation profile.
Does that mean then that you can hit an elevation, but pretty much all the customers have to have that same elevation? Or does it mean that, say like for example, a 0.75 degree beam or something like that, is that achievable?
Like if a given beam tilt will be relatively consistent across the bandwidth, but you might find it is fixed at say 1 degree or something, or half a degree.
So you're saying depending upon channel, it may change things. Is that what you're saying?
No, I think depending on the total bandwidth that you want. If you only want 40 megahertz, then maybe we could say, well, we can give you a beam tilt from anywhere from 0.3 to 2 dBs or 3 dBs, and it will be across the bandwidth. It will be relatively consistent. There may be a slight change, but it will be pretty consistent. But the design will fix to within a range of that. As you go more and more bandwidth, then we kind of tell you what the beam tilt and the null fill will be to achieve that bandwidth, as opposed to you tell us what beam tilt and null fill you want. And it's like anything, is a compromise. You push in one direction very hard, you get what you get. If you're willing to compromise on a bit more, then we can be more flexible in other parameters. The main benefit of why a slot antenna is so important is it's a very small antenna. It's a pipe that's 6 inches in diameter, maybe 10 inches in diameter, depending on the power rating. But that's the entire antenna. We can have different azimuth patterns. We can have near omnidirectional patterns. We can have directional patterns and everything in between. A panel antenna like this can also provide similar performance. Probably has slightly more azimuth control. But as a physical device, this thing is 4, 5, 6 feet across and weighs a lot more. So for a typically equivalent gain and performance, the slot antenna is probably 20% of the weight and wind loading. So if you need to put an antenna up which will allow you to change your main antenna, so an aux antenna, this is something that will very likely work on your existing tower without having to do a lot of structural work. It's very relatively easy to install. There's not so many parts. If you have a big panel antenna, there's many cables, many panels to install. So it should be cheaper and easier to install, more likely to be able to install on your existing structure without a lot of work. And yet you're still getting good bandwidth. The gain characteristics are very similar. You still also have a level of azimuth control. And the very nice thing also with a slot antenna is we can do an elliptically polarized signal or circularly polarized signal, which, whilst I haven't talked about that too much, essentially what that does is, certainly for any portable device, so any device where you don't have a receiving antenna with gain, because you don't know what direction it's going to be in, then having some energy in both the horizontal and vertical polarization greatly improves the chances that device will get the signal. It's very much a polarization issue. If you have a handset with no gain, you don't really know what the polarization of that handset is. So if you're completely out of alignment, you're going to be 20 or so dB down. But if you have energy in both the horizontal and the vertical plane, then you're never not going to be out of alignment. So you're always going to get some sort of signal. And the very nice thing with a slot antenna is to add that element of V in there is a relatively simple process. It requires some engineering, but in terms of parts, it's only a very small change. And unlike a panel antenna, if you do that with a slot antenna, it's the same feed system. We basically just couple in from the horizontal to the vertical. If you, normally in a panel antenna, if you want a circularly polarized or elliptically polarized solution, you normally have two separate feed systems within the antenna, which adds maybe 30-40% to the cost as a minimum, but it also it doubles the point of failures and the installation costs and everything, because it's almost like buying two antennas that just the panel happens to be in the same location. We still provide elliptically polarized or circularly polarized panel antennas, and that's not a problem. But certainly for an aux antenna where you want to get it up quickly and you don't want any hassles, you don't want people making mistakes in the installation, which is going to cause you problems, it's a very good solution. We've provided these in Chile and Honduras and Argentina, I think, a number of locations where we've provided these, and they perform very well. The general feedback has been that where the antenna is installed, often in a lower location with a lower transmitter power and a lower ERP, it's actually performed better than some equivalent antennas in similar locations. And I think probably largely that's to do with the elliptical polarization, where you have a very built-up area. That extra V is just going to improve the chances of where you get the signal in with all the reflections that go on. But as an antenna, it still gives good bandwidth, so you can put multiple stations up.
Gary, you know anybody in town running anything other than horizontal only?
Yeah, I believe WXIA.
Well, that's VHF. I think that's
Yeah.
horizontal only. And Gannett went all back to horizontal.
Oh, they did?
Yeah, we pulled it
Okay.
down
Then I
here and
don't-
everywhere.
I'm not aware of it.
They were full CP on channel 11
Mhm.
with a 100 kilowatt transmitter.
And the discussion we had earlier was about going elliptical or circularly polarized. You're licensed by your horizontal polarization, so adding the V is kind of for free in terms of a licensing. It does mean you'll have to get a transmitter that will be up to double the power if you went full CP to maintain the horizontal levels. But you don't have to go full CP. We think as long as you have a certain amount of vertical polarization, you get the benefits. Even 20% makes a huge difference. So you may only need to get a 20% higher gain antenna or higher power transmitter, or a combination of the two to maintain your ERP, but put a level of vertical polarization that's going to give you the increase. This is another project we've done in Panama, which was had broadband slots. It also had some panel antennas. It also had some channel combiners, and it's typical of what we've been providing in a lot of locations. Now this is a project we completed a few years ago. Some people who know Jampro is fairly well known, but a lot of people, if you ask them, say, oh, well, we're kind of a medium power FM company. Well, this is a TV UHF project where we supplied a 400 meter or 1,300 foot tower. The tower itself is we call it a hybrid tower, but the tower is actually fairly interesting because it's a guide structure. So obviously with a guide structure, the guy wires go out a long way. They go out almost as tall as the tower is. So you need a large amount of space to put the guy anchors in. This project, as you can see from the antenna, this is the antenna on top of the tower. It's in the middle of the town. So land is pretty expensive and there's lots of buildings. So one of the ways that we reduce the land area on the site is we put a secondary structure around the mast. It's not easy to see, but essentially the tower leg, one tower leg is here, and you see a larger triangle. And what this does is where the guy wires angle down, they get to a point, I think it's 300 or 400 feet above the ground surface, and then they go vertical. So instead of pushing out all the way, it brings the size of the site, and that reduced the area quite significantly. Why that was particularly important is this particular customer, when he had the plan to do this project, as I said, there was no space available. So he started buying up properties in where he wanted to put the site, and he kept it fairly quiet because he didn't want lots of people knowing. And he actually leased these out to his employees over a period of time. And once he bought up every single property, he cleared everybody out and knocked down the buildings, and that was his site. So obviously, if we had a full guide structure, he would have spent another 5 years and had to spend an awful lot more money buying property. So this was just one of the solutions that worked very well for him. So on top of the tower is a 32 lambda broadband panel array. This is combining 5 channels, all UHF. There's 2 analog channels and 3 digital channels. Now, because it's broadband, with that sort of power, the only really medium that would take that in a single run would be waveguide, and even that would be pushing it with 320 kilowatts. But the problem with waveguide, and to a lesser extent coaxial rigid, is they're not fully broadband. Waveguide is quite bandwidth limited. Coaxial less so, but the issue is that you install them in sections on the tower. Each section there's a flange, there's a small mismatch, they all add up, which means that, okay, you get good impedance on one frequency, but then you change to another channel, those flanges all add up and you have a problem. Yes, you can vary the length of the rigid and you can try and smooth that out, but maybe 2 channels you get away with, but 5 channels it becomes a real challenge. So in this scenario, and this is very common to most of the world, to be honest, is we use coaxial line. But we use 4 runs. It's not a big deal. 4 runs of coaxial line is probably the same wind load as waveguide anyway. By the time you put it in, waveguide's pretty big. And so you just have a connector at the top, connector at the bottom, and it's broadband. And again, for a lot of these broadband solutions, I can see coaxial line is going to be important, just because it is broadband. You know, there's no point in having a broadband antenna if you're going to feed it with a bandwidth limited line. So this system, as I said, the total transmitter power, this is transmitter power, not ERP, was 320 kilowatts. And there was one channel which was 180 kilowatts, a single analog channel, 180 kilowatts peak sync signal. And on this antenna, the ERP was almost 10 megawatts, which we think is probably the highest power UHF in Asia, if not one of the highest in the world. So people think that Jampro doesn't really do TV, or certainly not high-power TV. I beg to differ. I said, as well as the antenna, we provided the combiner system. This was a waveguide combiner. That's not a problem because each combiner is a narrow band, but the output was a wide band enough. Other projects that we've been involved with, this is an Alan Dick project. This was where we provided a tower, an antenna, a transmission system, and a combining system. It's a typical kind of height, 160 meters, 500 or so feet, where again, we supplied the tower, we supplied the antenna system, transmission lines, and all the installation and commissioning of that. It's another project in Vietnam, in Ho Chi Minh. Again, this was over 800 feet tower, providing antennas and combiners for both UHF and Band 3 systems. There's 2 systems. Provided the tower with elevator as well. It is, yes. So that's me there. That's me there as well. So yeah, that's above Ho Chi Minh some years ago when I was younger and thinner. And that's what the view from the top of the tower looks like, if anyone's interested. It's actually, in hot climates like that, it's actually quite a nice place to be because it's not as hot there as it is on the ground. It's like having natural air conditioning.
Ho Chi Minh City was Saigon, right?
Yeah, Saigon, yeah. For the airport code is still SGN.
Is it really?
Yeah, that's right. That's about the only remnants of Saigon that's left. But yeah, interesting project. We were only allowed to ship the steel in at night time just because the trucks were too big. The site access was a single lane road. And when we started off, it had a lot of telephone lines dangling over it, so we had to get those moved out of the way. And the area is actually completely surrounded by buildings. There's a university on one side, there's an existing broadcast studio on the other. So just storing stuff to do the installation was a nightmare. We had to bring parts in as we did the installation. And it's a fairly robust tower. I think the legs on this were maybe, what was it? Maybe 2 feet in diameter pipe, 1.5 foot diameter pipe at the bottom, with some fairly large flanges. And it's designed to take 3 antennas, UHF at the top, then VHF in the middle, and then an FM antenna at the bottom in the future, if they go that way.
State broadcasting?
It's HTV, which is, I guess the most state broadcaster is VTV, which is Vietnam Television. This is Ho Chi Minh Television, so in the south, they have full coverage in the south, as you can imagine. But yeah, everything's kind of state in Vietnam. They're all connected some way or another. but it's the biggest broadcaster in the south. So this is a project for VTV, the other broadcaster. This was just supply antennas and combiners in various locations around Vietnam. As I said, typical sort of installation of what we would do. This is in South Korea, which was provided quite a long time ago. This was ATSC, well, ATSC 1 it would be, when they first went digital. I guess the interesting thing on this, I don't know if you know Seoul, but there's a hill on it called Namsan. I think that means a hill called Nam being hill. And at that location is a kind of lighthouse type structure with a rotating restaurant and a tower on top. But this antenna actually is on the tower that's next door to this structure. So it's the first time I've been up a tower where I had an audience, which was a bit surreal, where as people tuck into their, I don't know, noodles or rice, you're kind of waving at them and they're wondering what you're doing. So obviously this picture here was taken from inside the restaurant, but that was the first for me, having an audience. Makes you feel a little bit...
Right in the aperture.
Yeah, right in the aperture. So, you know, we can cook the food as they watch you. So they didn't seem to worry about that.
Our own Korean barbecue.
Yeah, exactly. It's a new Korean barbecue. And soon they'll maybe get a UHD Korean barbecue from it, no doubt. So, the slightly weird thing about this is actually 4 antennas. It looks like 1, but it's actually, and this was, according to the spec, we didn't define this. They actually want, this is KBS1, KBS2, SBS, and NBC. And they wanted them all separately and not combined. Don't ask me why. Which is the reason why you might be able to see the panels are slightly tilted out. So that's the only way you can put null fill in a 2-bay antenna. The only way to put null fill is to physically tilt the panels. So that's why we actually did that. Normally you just do it with phasing in the cables, but you need at least 3 bays to do that. So this is an ongoing project that we have almost finished. This is a 500-foot tower in Jordan. Where turnkey project, we provided the tower, we provided the UHF and FM antennas, which also come with frequency combiners, 8-channel FM and 6-channel UHF. And this is, as I said, the tower was completed earlier this year. The RF system is on site. We're in the process of going in, installing and commissioning the system. So some of these projects, you know, we don't do massive structures 1 a week. It just doesn't go like that. So some of these projects are a few years old. This is a very current one. And we typically do projects like this, probably on average one or two a year. But you know, they're long-term projects. The tower takes a long time to manufacture and install, as do the antennas. And maybe 6 months from order to completion, maybe longer, maybe 9 months. Any tower installation, especially internationally, there's plenty of issues just importing the product, but there can be weather issues and all sorts of things that can delay a project from maybe where the plan was. But as I said, we're normally doing a project like this somewhere in the world. This is some of the UK installations that Alan Dick were involved with. I guess this is interesting because this is a 5-around antenna. In fact, Alan Dick has supplied some of these 5-around systems in the USA in the original digital projects in 2000 to 2004 or 5 or something. So why a 5-around rather than a traditional 4-around? The main benefits is it gives you more space inside, so you can put more cables up it and still maintain space to climb through. All of the Alan Dick antennas had space to climb through. There's a ladder here, and you can climb through the aperture. You don't have to turn the antenna off to get to the light at the top. And in fact, in the UK, one of the requirements that most of the antennas, you could climb through them fit full RP, and they would be RF shielded to the point where that wasn't an issue. So again, typical installation, 5-around, 12 tiers, many channels, and you still have access. And then this is another thing that was done a lot in the UK. We call it a wraparound. It's actually this antenna here. And this was really to maintain a given azimuth whilst they wanted to change antennas. So the top antenna up here was originally an analog antenna. They needed to get the digital services on, but the antenna was already maxed out. So they would do this wraparound antenna that would provide the initial digital services, but also had the capability to handle the analog services as well. So when it came to doing the final change, they would put the analog services and the digital services on this, which was typically 5 analog channels and 6 digital channels, so 11 channels combined into here. Then they could remove the top analog antenna and replace that with a final digital antenna. But they kept the wraparound antennas because they were a backup to the main antenna. So after all the project was finished, they had 2 antennas on a lot of these locations. Now, as I said, all the sites in the UK are all owned by Arqiva, so they have multiple channels. So there's, per frequency, you can proportion up the cost of doing that, and it makes some sense. If you're just a single channel, that would be an expensive way. I'd recommend doing a broadband slot antenna instead. But for the UK and what they wanted, that suited their particular need. And there's multiple installations of these wraparound antennas, from anything from 12 around to 18 around to even 21 around. So these, they're big panel arrays. They're pretty expensive, but it suited their need. Here's some of the projects that we completed not that long ago, a few years ago. This is in New York. This was a channel 3 antenna. This is an Allen-Dick antenna, designed by Allen-Dick, but actually manufactured in the US by Jampro. So very much the 2 companies working together. So this is on 4 Times Square, which is some more familiar than the others. If you're not familiar, if you've seen Teenage Mutant Ninja Turtles, it's the tower that falls down. Now, that wasn't us. We don't use Ninja Turtles as riggers. They might be quite good though, and the tower didn't fall down during the installation. But it's pretty hard to see because it's everything's very large. But the antenna is this antenna, the very top antenna. So this was a channel 3 antenna called the Lambda. It's circularly polarized and very omnidirectional, and it plays really well in the New York market. I think the feedback we got was it's probably the number 2 channel in terms of reception. I think, again, CP top mounted.
What's the programming on that?
That I don't know, actually. I don't know the program on it.
It's not the big network stuff. I didn't know if they were independent, or is that some sort of foreign language, ethnic, multi-channel stuff?
I don't think, well, I don't know the program, to be honest. That's something we can find out.
I'll have to ask John. I'll see him tomorrow.
Yeah. I'm sure he'll know better than I would. The other interesting thing about this project is being on top of a building, access is limited. All of the parts of the antenna had to be fit in an elevator. I think the largest part was maybe 10 foot high. The antenna, again, is difficult to see, but basically there's a central pole, and then there's some dipoles that go around the pole that are slanted. So the pole had to be broken up into many sections with flanges to fit in.
It was a big tower usage after World Trade came down.
Yeah.
A lot of people all lived up there.
Yeah, that's a very big structure. I think our antenna, 6 bays at channel 3, I guess the base spacing is going to be, what's that, 6 feet or something like that, or maybe more than that, I suppose. No, it's going to be 5 meters. Sorry, it's going to be like 15 feet, isn't it? The base spacing. So the total antenna's, I guess, what's it going to be? 15 times 5 or something like that. It's pretty big, 80 feet, something like that. So yeah,
Big antennas on channel 3.
yeah, big antennas, and look, considerable weight as well. Probably not that considerable compared to the weight of the total tower. But yeah, to give you an idea of the height, I think each of those kind of those antennas are about 80 feet or so. It's typical. We've also done projects on Empire State. Both Allen-Dick and Jampro have provided systems there, and the CN Tower in Toronto. And these are just sort of more there for the buildings they're on rather than necessarily the systems that were provided. But the one project that I wanted to focus on a little bit in more detail was a project we did in Singapore, where we did a main site installation, which is maybe more typical to some of the projects I've shown. But we also did a follow-up project for some boosters, gap filler sites, which is, again, because it's a single frequency network and what they were trying to achieve, that's what they wanted to do. The goal there was to try and have in-building coverage pretty much all over Singapore. And the customers, the main Singapore broadcaster, there's really only one, but the station is either an affiliated or owned by Fox, actually. So the main site, the system was to cover most of Singapore. It was a turnkey installation, providing antenna, combiner, transmission line, patch panel, monitoring, and we installed and commissioned all of that with our own team in Asia. So the panel was, as I said, it's a panel antenna, fairly large, 12 bays, 48 panels, horizontally polarized, had about 100 kilowatt power rating, which is not extraordinary, but still fairly reasonable. The system was designed for DVB-T2, although in the initial installation it was handling some analog channels and some DVB-T1 channels, so they had 3 standards, not just 2 standards to worry about. They're still trying to switch off the analog, and at some point they'll have to switch off the T1 as well. We first did T1 in about 2000 with them, so give you an idea of how long these things take to turn off. You know, they're looking at 16 years where they've had digital and analog on. So broadband antenna installed on a 224 meter, so 700 foot or so tower. The tower was originally provided by Alan Dick in the 90s, and the first antenna was provided by Alan Dick. And we replaced dual transmission lines. So again, there's me on top of the tower, looking down. And as well as the antenna, we provided a combiner. This is a 6-channel combiner. The typical power rating was about 6 kilowatts average for the digital. Whilst we ran some of the analog channels were about 20 kilowatts, but the 6 kilowatts digital, it still had enough headroom to handle the analog of about 20 kilowatts until they converted to digital. Again, maybe not so easy to see, but all of the modules were designed on the same principle. They were all adjacent channel combiners. Whilst they weren't all actually physically adjacent, the combiners themselves would be able to handle adjacent channels if needed. There's miss one, and then 3 continuously together, and then push out further, and there's another channel. As well as providing the channel combining, the filters involved in these combiners also provided the full mask filtering. So there was no mask filter provided with the transmitter at all. The mask filtering and the combining was all done in the combiner. So that saves you a filter. And also it saves you some losses. Rather than putting two filters in series, you can put it all in one. That makes the filter design maybe a little bit more challenging. And the way we maintained very low loss was we used waveguide filters. These are elliptical filters, and they use circular waveguide. So they're 8-pole filters. You can see there's 1, 2, 3, 4 cavities, but because they're dual mode, essentially each cavity has two sections in it, has 2 poles in it, orthogonally. So you have one resonating this way, and then you couple to this way, and then you couple through to the next drum, and so on. So it's an 8-pole filter with cross-coupling, which allows us to get very sharp edges to allow us to do the adjacent channel and the mask filtering. The DVB-T they were using was in extended mode, and that makes the filtering even more difficult because extended mode means they push out the bandwidth very slightly. They really push to the very edge of, in this case, this was an 8 megahertz spectrum. That's just the channel spacing in Singapore. But they very much push to the edge of the bandwidth that's available. So that makes even more stress on the filters to work properly.
Are the mask filters the same as the FCC curve?
Well, no, this would follow a DVB-T mask, which is different to ATSC3. But in terms of when you account for the reduction in bandwidth, it's similar. We would probably use physically the same device. We would just tune it differently. Obviously, we'd tune it for a narrow bandwidth, and
See, the mask filter is a high power filter after the transmitter, and say like in the case of Gary's, it's a single channel.
Yeah,
30.
correct.
It's 110 dB down, 6 megs out or something.
Well, the filter's not 110 dB down. It's 110 dB down in conjunction with the transmitter. The filters normally only give about 60 at best when you're far out, but close in it's mainly only 40 or something. So the mask is a combination of what the transmitter does and what the filter does. Obviously, the transmitter, you don't want it to produce energy outside of the band, but it just inherently does. But the processor can drop the outside of the band down by 30 or 40 dBs. It depends on the manufacturer to give the exact number, and then the filter tops it up to meet the actual mask spec. So any mask filter has to be done a little bit in conjunction with the transmitter supply. I mean, the transmitter suppliers all meet what they can do, and the filters do what they can do, and it works. But technically, the mask is a combination of the two. But in this case, rather than putting the filters outside, because we needed adjacent channel combining anyway,
sure.
That almost meets a mask spec anyway. You just add a little bit more, it meets a mask spec, and then you only need one filter. But these, I mean, the loss, the individual module was probably 0.22 to 0.25 loss, which is pretty low. And that's mask filter and combining altogether. Now, the mask filter alone would typically be more than that. So these were very low loss solutions. So these are constant impedance combining. So you have a narrowband and you have a wideband port, and you chain them together. So that they're kind of like N+1 systems essentially. So you have your narrowband channel, and then you add on to whatever's going into the wideband. So if you put 6, you add 1 in each time. In Singapore, they love redundancy, and so rather than having a single 6-channel combiner, they had what we call dual 6-channel combiners. So this is a single module, and this is 6 modules on a line installed, but above that is another 6 modules installed. And what they do in Singapore is they run, so both of those are identical combiners. So each module's tuned to a given channel, and they're in pairs all the way down. And in a normal situation, they'll feed through this 6-port patch panel, which has got a splitter on it, and they split the signal from the transmitter upper and lower in the combiner. And that goes all the way through to the antenna. So you have, instead of just upper and lower antenna and transmission line, you have upper and lower combiners as well. And that's purely for redundancy. If there's a problem anywhere in that chain, antenna, transmission line, combiner, they can turn the whole thing off and transmit just through one combiner chain. In fact, this particular system, on the output, you can't see it from the photo, but on the output, they had a large 6-inch patch panel splitter, so that if you were forced to use one combiner chain, you could still split and feed both half of the antenna. So you wouldn't lose 3 dB on the antenna gain. And as I say, they love their redundancy, as well as providing essentially a backup combiner, except it's on air all the time. So the good thing about that is you know it works. The problem with these backups that are switched off, in the big panic when you need them, you switch them on and you find they haven't been used for 5 years and they don't work ever. Whereas because this is active all the time, you know that it's fundamentally working. So as well as having a backup combiner, in Singapore they really only have one main site, but they have 2 towers on that site. And on the other tower there's also a UHF antenna and a combiner in a different building about 400, 500 feet away. And we provided a system that could pipe the output of this combiner through about 400 feet of 6-inch rigid line to the other side of the building. We then provided another patch panel there that linked into the existing antenna. So this combiner can go to the antenna we installed. It can also be directed to another antenna on another tower. And the combiner in that building can actually be directed across and go to the antenna we installed. So they essentially have backup tower. And as well as their UHF system, and this is systems that I've worked closely with them, with Alan Dick, the VHF and the FM systems have that as well. So they have ability to turn a tower off and put all the services on one or the other towers in either direction. To give you an idea of the number of channels, they have about 10 UHF channels, 3 VHF channels, and 15 or 16 FM channels, all transmitted from this one location. And they're all combined systems. So each tower has 1 UHF, 1 VHF, and 1 FM antenna. So they're pretty packed sites. They're not small. So anyway, the combiner was critical mass, low loss, and designed for actually 10 frequencies in the future. We've since gone back and added a 7th frequency to this combiner. And here we can see this is like the patch panel. We call it a cross-site patch panel because it links from one building to another. And we provided monitoring and for VSWR and power monitoring. That could be.
So what's the channel bandwidth there? Is it 6 megahertz or wider?
8 megahertz.
8.
Yeah.
Okay.
It's a bit UK system, being a ex-British colony. They kind of followed that system. And most of the world.
In Australia, 7, and the rest of the world 6.
Australia, they're just awkward, so they're 7. Most of the world is either 6 or 8, and I would say, okay, America's a 6. You know, Latin America predominantly 6. Obviously North America 6. Korea's 6. Nearly everywhere else is 8 megahertz across the board. Europe's 8 megahertz. Africa's mainly 8 megahertz. Philippines is 6. But again, that's
What they said about the U.S. and NTSC.
never the same.
World's first and worst.
Oh, first and worst.
Never twice the same.
Yeah, never twice the same colour. That's how I heard it. Okay, so this was the main site. Great project. But as I said, the key thing here was they were looking at what could be done with a single frequency network, because they're really looking at in-building penetration. The one site, whilst it covers all of Singapore, it doesn't necessarily get inside every building that's in Singapore. So they realised they would need some repeater sites. There's a lot of high-rise buildings in Singapore, or fairly high-rise, maybe not ultra high-rise, but 30, 40 stories. One of the issues, all of the buildings are about the same height. Everywhere in Singapore is near an airport because it's not a big place, and so the height restriction is very much fixed by the airport. So they tend to build to that height restriction. So you don't have one building that's taller and you can get in. They're all the same sort of height. So it's almost like having two ground levels. You have the real ground level and then you have the rooftop ground level, which makes an extra challenge from an RF point of view. So anyway, they knew they needed relay sites, and they thought, okay, we'd probably need maybe 10 relay sites. We'd try and put some omni antennas on various buildings. So this is where the main site is. This is Singapore total. It's about 35 miles this way and maybe 20 miles this way.
So what's the country to the north across the water?
Malaysia. Which a long time ago, it was all Malaya at one point, and then they separated after independence from Britain. So Malaysia's a much bigger country. Now obviously our antenna doesn't cover Malaysia, because I'm not allowed to say it does, but it doesn't cover Malaysia. It only covers Singapore perfectly. But anyway, the site's in the middle, and it covers Singapore fairly well. But with all the high-rise, etc., as I said, they need these relay sites. So to give you an idea, 10 sites were dotted around Singapore. There's some hills actually in Singapore here, which does put shadowing out at this range, which is why a lot of the relay sites were here. The airport's over here, but there's another military airport over here. And that kind of covered particularly where people lived. This is the kind of business district. They weren't so bothered covering this because this is offices. But most of the areas, the outlying areas, are where people live. So the idea was they'd put 10 sites up, omnidirectional antennas. Some of the problems they had is they couldn't put them on the building rooftops because they've got a height limit. So then they say, okay, we'll put them on the side of the building, but you don't want to put an omnidirectional antenna on the side of a building because you're going to get reflections off, and that's going to cause. So they said, okay, we need to change that, have directional antennas. And so that changed their plans a little bit. Anyway, they put the 10 sites on air, and they went, okay, that's nice, but we still had some problems. So they needed some more sites. And so we went from sort of phase one. Anyone want to guess how many antennas, how many sites they ended up with currently? It's still an ongoing project. Any ideas? It's not a big place. It's only small. Anyone? Anyone want to guess?
Dozens?
So 120 sites.
10 dozen to be specific.
Oh my.
Yeah. So just if I flick back and forth, you can just about see the red dots that come on there. And part of the reason was because they couldn't put omnidirectional antennas on top. Part of the reason is if you have a line of buildings, once you hit the first building, you're 20 dB down or something. So you can't do much with that at that point.
This is all same programming, SFN?
All the same programming, SFN, so it's all the same frequency. In fact, the relay sites had 4 digital channels on air. So every rooftop, because these are all rooftop installations, I'll just show you what
do they all take the main feed, or they?
I'll talk about that in a minute. So I'll just talk about this is a typical installation. It's a small panel antenna. In this particular case, they wanted vertically polarized panels. So the main antenna is horizontal. All the relay sites are vertical because they felt that would. They could have gone CP, but they felt this was the simplest, cheapest way to get it into the buildings because they realised how many sites were going to be in there. So this is one of the larger panel sites. This is 6 panels. I think the most we did one site that was maybe 16 panels, but the typical average is probably 6. Some sites were 1 or 2 panels only. But these are low power. These are mounted off a pole, some sort of directional pattern. And on every one of these sites, they were all on rooftops. You would have 4 transmitters, typically in a weatherproof container, and you'd have a 4-channel combiner also in a container, and then that would be piped through to the antenna. And the way we work with them, because the sites, the numbers obviously got very large, they had different coverage. Sometimes they wanted to cover 270 degrees, sometimes. So we came up with a kind of matrix of different types of antennas, and they would, per phase, they would order 15 or 20 antennas. And then, because the installation was going on and on, they installed them locally, but we would go in and test and commission them. So they maybe install 10 sites, we'd come in, commission them all, make sure everything's good, and then they'd turn the system on.
So what transmitters and power level were
If we just go back, the original sites were, they're relay sites, but they were actually low power transmitter sites. They had proper links. They had fiber links that were properly synchronized. So from a network issue, very easy to set up. They can set them with exactly the same timing as the main sites. All the signals are synchronized, no problem. But to do that for many sites would be very expensive. So the 120 sites were all fed by RF frequencies. But because they had a lot of frequencies in Singapore as a broadcaster, they are actually fed by different frequencies. So they're not actually on channel repeaters. But the clever thing, they have 4 transmitted frequencies with a kind of fairly robust signal because they're trying to get in building, so they have as robust a signal as possible. But to feed each location, they use 2 other RF channels. And so a given RF channel was the maximum bandwidth that the DVB-T could do. It's a 64 QAM signal. But that signal's not very robust, but it didn't matter because on each receiving site, the broadcast engineers could set up a good directional antenna. They could pan that in, make sure the signal's really good, and they had full control over that within their network. But the great thing about it is a given 8 megahertz channel could hold enough data to feed 2 of what they were actually transmitting on the rooftop. So, okay, they have 6 channels, but 2 of the channels are the feed, and then the 4 of the channels are what's actually being transmitted. But the great thing about it, it's a very cheap way to feed the sites, because it's in a network they already have. In fact, the 4 feed channels are actually transmitted from a separate antenna to the one we installed. We went back and installed a 4-bay antenna at a later date, and that's used to rebroadcast as a feed for all of these stations.
Transmitter, TPL, and manufacturer.
The relay sites were 500 watts to a kilowatt. I think they were kilowatt capable, but they would generally run at between 500 and 800 watts. I believe they're Rode, actually. They like Rode in Singapore. All the main transmitters were Rode as well. But for the low power stuff, it was a low power manufacturer, for want of a better word. So not one of the big companies. I'm trying to think. We didn't actually provide the transmitters. That was a separate
I
contract.
was just curious.
It was
European?
yes. I think Italian. Not a telco. Or maybe it was a telco. No, not Thales. I can look it up. I can remember.
No,
But when you get and the low power are like 100 watts, which are very similar to telco levels, maybe a little bit more. And if anything, they turn them down. The other issue they have RF hazard issues. I remember some of the earlier sites. There's a guy, he's measuring the RF hazard on the rooftop, and I said, "Oh, is it too high?" And he said, "Well, yeah, it's too high, but we haven't actually switched the antenna on yet." I was like, okay. So you have a great situation where they need coverage, but they're not allowed to increase the RF level. So there's various issues involved in rooftop installations, health and safety issues. But again, that also indicated why they had so many sites, because they were maybe limited in total power. But they actually find the main problem was if you fire into a building, it doesn't matter how much power you put in it, there's not much going to come out the other side. And if you have a lot of buildings all stacked together, then you just need multiple sites. You can see a lot of these locations, they're all very close together. It's not like they're spread out. So they said, right, we need to cover this. This is where all the buildings are. And you very much had a situation where you had a building with an antenna firing into this building, and then this building would have an antenna firing into the original building and almost crossing over so that they can illuminate the whole side of the building. And you almost need another building to cover the other side of the building. So some buildings were being illuminated by multiple antennas. I said this was a typical antenna, and this is a typical installation. So the buildings nearly all had water tanks or elevation shafts above the main building. So this is the kind of the water tank. So we'd put a pipe on the side and just put the panels around. Had to follow health and safety in the installation, and we coloured it even. And that was a typical installation, as I said. But the key thing there is there's a lot of sites that were used, but very low power. And again, because the frequencies were combined, again, if you want to do an SFN, putting 120 sites in is expensive. But if you only pay a quarter of that cost because you share with other broadcasters and combine the signal, then maybe it becomes more attractive. You probably don't need 120, but it really depends on what you're trying to achieve. If you're just trying to achieve rooftop reception, you won't need 120. It might only be 4 or 10 sites where you just want to boost up on the fringes. If you care about deep coverage, then you're probably going to have more of a cellular type solution, which is maybe not surprising because it's a very similar signal to the way the cellular networks work. And that's pretty much the end of the presentation. But it's really just to say that...
That's Hancock Tower.
Yeah, that's Hancock, where Jampro's done some stuff over the years. And that's Salt Lake City for FM, where we have...
Farnsworth Peak? Salt Lake, that's where the TV is.
I think that's Salt Lake, isn't it?
It's Salt Lake, but I can't remember the name of the site. But that's where we've got something like 13 FM and 7 HDs on there. on that one site. So again, this is a combined system. Again, broadband systems that Jampro have done in the USA. I know not so common.
So what was the far ones?
That's just a slot antenna. Oh no, sorry, that's just a JMPC, which is probably our most famous FM product. The most copied antenna is a penetrator antenna, but when we go out and visit customers, particularly in Asia, it's the imitator, because a lot of people have copied us. Imitator. And actually, I don't know what that is. Yeah, I'm not entirely sure. But the key thing to note is if people think we're a low power FM company that don't do a lot, we internationally we do some real high power UHF projects that are broadband and elliptically polarized, and we've been doing this for years. You know, some of these projects are almost 10 years old, still working fine, and the customer's been very happy. So our experience internationally is huge, and very relevant to certainly ATSC3, where we've essentially done that. We've dealt with the type of signals that are going to be used and the type of products that are going to suit for what you can do with ATSC3. And that's kind of what I'd like to say. So thank you for your time.
Yeah, thank you guys for coming in and sponsoring the meeting. Take care, Dan. I appreciate it.
Do you want to do your...
I'm actually going to edit that in just